steps, but they can give away multiple hydrogens. They just don't do it all at once. All right, moving on. Another good question, and you may have asked this question to yourself when I was talking about acetic acid earlier. Here's a great question. How do you identify which hydrogen is acidic if you have a molecule where some hydrogens are acidic and some aren't? Example, acetic acid. What we just talked about, this is an organic acid. Well, we have 4 hydrogens in this molecule. But what you see is that 3 of them are not acidic. The 3 that are attached to carbon are not acidic. Why is that? Well, if we read these statements up here, only those, meaning only the hydrogens bound to electronegative atoms. For example, electronegative atoms could be oxygen, could be fluorine, could be chlorine, could be nitrogen. Okay, nitrogen is another one. Sulfur is another one. These are all electronegative. How do I know when an atom is electronegative? You have to have an electronegativity chart. Anything kind of close to or around fluorine on the electronegativity chart is going to have a relatively high electronegativity. And when you have a hydrogen bound to an electronegative atom, so if you have a hydrogen, I'm just going to say X here. And if element X is electronegative, but it's an electronegative element, then this bond between H and X is polar. Okay, so the bond here is polar. Okay, again, you could go calculate the actual electronegativity difference and make sure it's above 0.5. But when you have a polar bond, then what you end up with is a hydrogen that is positively polarized. Okay, and you should be familiar with this language from talking about hydrogen bonding. Okay, what that means is we know any polar bond, there's 2 electrons here, 2 electrons in this polar bond. That means the electrons are pulled towards element X, the electronegative element, making this partial negative and hydrogen partial positive. Okay, anything we say is partial positive is electron deficient, because we said the electrons are shifted towards X. This is an uneven tug-of-war match, okay? The electrons are pulled harder towards X because electronegativity means that atom or element wants electrons. It likes electrons, okay? So that's how we identify when a hydrogen is acidic. If it is a partial positive, a positively polarized hydrogen. Remember, hydrogens bonded to carbon are never positively polarized. Okay, the CH bond is not polar. So that's why these 3 blue hydrogens are not acidic. Only hydrogens that are bonded to an electronegative element, such as oxygen or these that we've listed up here. Okay? All right. So that's kind of it for our talk on acids for now. We will come back to different properties of acids in a little bit, but I also want to talk to you about bases. So if an acid, remember we defined it as what? How did we define, what was the nickname we give to acids? We said they are proton donors. So guess what we nickname bases? Proton acceptors, okay? I'm going to read this first statement up here. When an acid donates a hydrogen, it has to donate to something, okay? This hydrogen is very reactive. It's usually not going to be found floating around by itself. It's going to join up with something. And that something is going to be what we call a base. Okay, it's a substance that accepts a hydrogen ion. So we nickname it a proton acceptor. So you've got acids, which are proton donors, bases, proton acceptors. In a lot of the reactions that we've looked at, guess what? Water was the base. For example, when we had HCl plus water, H2O, what did we make? We made Cl minus and we made H3O plus, the hydronium ion. Here, HCl was our acid, So by default, water was the base. Now I know I don't think of water as a basic substance. But you don't have to have something that's really strong. Usually bases, like common household items that are actually basic items, are very soapy things. So like detergents, soap, those are very alkaline, and alkaline substances are their bases. Okay, so we don't think of water as a base oftentimes because it doesn't have those same kind of soapy properties that a lot of common substances do. But anything that accepts a proton or a hydrogen ion from another molecule is a base. And so water can act as a base. Water, you'll find, is a very versatile actor. It can act like many things. Okay, water has multiple personalities. Okay, you'll never think of water the same way. Anybody know anybody from like high school had multiple personalities? I know it's a very real thing, personality disorders, but I don't know. I always like using that analogy with water because it can act like a base in some cases, and we're going to see reactions later on where water is going to act like the acid. Okay. Well, if we're talking about bases and we say water can actually act as a base, or anything that accepts a hydrogen ion acts as a base, what is the hydrogen attached to? It is attaching to electron. Oh, goodness. It is attaching to electrons, okay? Any chemical bond that forms between two atoms contains how many electrons, okay? Any chemical bond that forms, it contains 2 electrons. If we don't have 2 electrons, we don't get a chemical bond. All right? So lone pairs are, guess what? 2 electrons. They're great things for a base to have. So a base has to have a lone pair. Okay? Negatively charged ions, you'll always find that those things have lone pairs. So what are some examples of some bases? Okay, hydroxide ions, OH minus. These are excellent bases. OH minus, this is a strong base. In fact, it's one of the strongest, maybe the strongest base we know. Okay, now OH minus doesn't usually sit around by itself. It's usually, because it's an anion, we usually see it as an ionic compound. So it's got some sort of cation attached, and that cation, in this case, we see some examples, could be lithium, could be sodium, could be magnesium. So commonly the cation attached to our strong base before the acid-base reaction happens is some sort of main group 1 or main group 2 metal, all right? And it's this substance as a whole, okay, cation and anion, that we call the base. But really, the part that's acting like the base is just the OH minus. We're going to find the cation metal. Here, the examples we're given are lithium, sodium, magnesium. You could have calcium. Okay, they don't participate in the acid-base reaction. I'm just going to abbreviate acid/base reaction. Okay, the cation metal, so many different examples, but they don't participate in the acid-base reaction. They're just kind of a placeholder. They're balancing out the negative charge on the OH minus. So they're part of OH minus. They are part of the compound we call the base, but they're not actually the thing that's acting like a base. They will, in solution, anytime you have these kinds of ion or compounds in solution, what are they going to do? They're going to break up into their cation and their anion, okay? They'll be aqueous. And so the metal part will not participate in the reaction. It's just the OH minus. That's the actual base. I wanted to make that distinction and really drill it into you guys, because we call things that don't play a part in a reaction, we call them spectator ions. So all of these cations, these main group 1 and 2 that are usually part of an OH minus substance, like which is a strong base, we just call them spectator ions. They don't participate in the reaction. So if you look at these two reactions written here, the actual acid-base reaction is this top one. Here's the main thing that's happening. The OH minus is accepting the H plus, and what do you get when you have OH plus H? You make water, okay? If you'll remember, back in chapter 5, when we learned how to classify chemical reactions, we had to classify 3 kinds. We had to classify precipitation reactions. We had to classify redox reactions, and you had to classify acid-base reactions. And what did we say? We said anything that forms water is an acid-base reaction. And that is a very surface level, shallow. That was an appropriate definition at the time, but you actually see that a better definition is way more detailed. And actually we kind of lied to you. There are other acid-base reactions that don't form water, but they're still an acid-base reaction. So we'll look at some examples of those. But here is what's happening. When OH minus and H plus come together, they form water. That's the acid-base reaction. And you see here, lithium is just the placeholder. Lithium just ends up by itself. It's just